Lab number 2 focuses on data processing, especially statistical analysis, and it also transitions us over to diffusion, which will be our lab 3 topic. But let's take a look at the important terms first, and here's a set of statistical terms that you should take a look at and know. You might be tested on these statistical terms with like a matching set. That's typically what I do. But the first couple is probably something you're familiar with. The mean is the average. So you're adding up all the data points that you have, and then you're dividing by the number of data points, and that gives you the average or the mean. The range is the data set from the lowest to the highest value, and the mode is the number that occurs most frequently, and the median is the middle number. If you line up your available data points from lowest to highest, and then you look for the middle number, that will be the median. As we saw last in the previous lab already, in physiology you're dealing with individuals, and that means there is variation, natural variation, whether that is height of people or response to medication. We're not robots like that lab robot that you probably have gotten to know by now in Labster. That will not change, but people, there's variation. So in nature we have natural variation, and because of that, we need to run our experiments with groups. Either if you have an animal model, it would be groups of animals, or if you're dealing with people and you're testing, let's say, a new medication or new treatment, then you have groups of patients. So when you have groups, then you need to process your data by first calculating the average, and then you do your statistical analysis. And that includes taking a look at how much variation was there, and that is done with a standard deviation. A standard deviation is, one standard deviation is the plus minus the mean, or the average, that includes 2/3 of your data, so 66.6% of your data. The variance is a measure for how much variation there is in your data set, and the confidence limits, those are set sort of, there's a standard procedure on how you're supposed to process the data. So that will say with how much confidence you can say that there is or is not a statistically significant difference. The result that you want to come up with after you did all your calculations is the answer whether or not there is a significant difference between your control group and your experimental group. And for that, there are some rules to the game, like your confidence limits and how stringent you have to set this. In science, it's customary to set your confidence limits at a p-value of 0.05, and we'll take a look at that. The most commonly used analysis to compare two groups is the student's t-test. So a t-test, a two-sample comparison. And I'll walk you through the processing of the data in this and how to do a t-test. Presentation of data. The most common types of data tables would be a line graph and a bar graph. In physiology, a lot of times we have bar graphs because we have two groups, and then the height of the bar representing one group is the average, and then you have to add your error bars on top of that. That's plus minus the mean, that denotes the variation in your data set, and I'll show you that too. So graphing is it's much preferred over just showing summary tables, because summary tables is just a lot of numbers and it's not really clear what these numbers mean immediately. When you're graphing it and you have a line graph that shows a certain let's say you have a line graph like here, and you have a relationship. Here's your x-axis and your y-axis, and of course this is your independent variable on the x-axis, and the dependent variable is the y, so that's what changes. Usually the x-axis is a timeline. That's very common. This is a very ridiculous x, but anyway. So if you have, let's say, an enzyme reaction, you're producing product over time, then you might see something like this, a steep rise, and then it levels off, something like this. So that would be a typical line graph where you have continuous change. So product is continuously produced, and you get a continuous increase in your Y right here. So anyway, the other very popular graph would be a bar graph, where you're summarizing your two groups, and then you have, let's say, a control group right here, and you can include your arrow bars like this, and then you have an experimental group that's like this, and including the arrow bars showing the variation in your data set, and then you have to do some math to figure out whether or not there is a significant difference between these two data sets. So here this would be your control group and your experimental group. So that's a pretty typical kind of scenario. So those are the two most common types of graphs that you would encounter in science. There's also, of course, a pie graph, but it's not that common in science. And our last portion right here gives us a transition to the next topic, which is going to be transport, and that is mostly, we're talking about diffusion, osmosis, transport of materials across biological membranes. A term that you definitely need to know is rate. A rate is change per time. So let's say we're talking about diffusion, that would be how far something is diffusing, the diffusion distance per time increment. Surface area and volume, those are just mathematical terms that you can calculate with formulas. The surface area to volume ratio is important because when you're taking a look at cells, and you want these cells to be part of a tissue, and these tissues need to be able to respond, you want a very large surface area compared to a small volume. It's really important also if you want to take advantage of diffusion, which cells love to do. So if you have huge diffusion distances because your cells are extra large, then diffusion isn't going to work very well for you. But if your volume is small and your surface area is large, then diffusion is perfect because you have very small diffusion distances and you have a large surface area in which you can embed channels and signaling molecules and receptors and stuff like that. So we'll talk some more about that as well. So diffusion is the concept that's very important for the next lab, and we sort of transition to that topic at the end of this lab. And the extent versus rate of diffusion. The rate of diffusion is given by parameters such as temperature and also by concentration gradients. Now the extent is just a measure, so how far something has been migrating, but rate is really the important thing. And rate is a constant when the conditions are the same. In other words, if the temperature is given, then the rate of diffusion is for a given sample is going to be a constant, and we'll address that some more at the end. Let's take a look at what you're supposed to be doing in this lab. You get an introduction here, and then part A is talking about instrumentation, physiological variables. You got your definitions here for the statistical terminology that was also on the front page. It's a good idea to take a look at that, because that's easily testable material, and that I usually put that on your first quiz. The calculation of the t-test. There are some formulas given to you here that we'll be taking a look at. Then it's not necessarily the most conventional nomenclature to call the sum of the values of a data, to call it A, but it doesn't really matter. So most people will use that funny sign, this sum sign, and then it's just adding up the data points. So the sum of the values of the data, that's just given here. You're adding each data point up, and that's in this case here it's labeled A. Now B is the sum of the squares of the values of the data. So if you take each data point and square it, and then you add up these data points, that will be B in our case here, and that's the sum of the squares of the values of the data. And then C, this number here, can be calculated by comparing basically the sum of the squares to the square of the sum of the data. So that sounds kind of funny, but that's what it is. B, remember, is the sum of the squares, and A is the sum of the values. Now if we square that, then we have the square of the sum of the data points, and we have to divide here by the number of data points that we have in our set. The average is always calculated by the average, that's X bar, and that's customary to call that X bar, is equal to the sum of your data points divided by the number of samples that you have. And the sigma, the standard deviation, is calculated with the following equation. You take your C value that you just previously calculated and divide by n minus 1. And that will give you the variance. And then so the variance, that's basically the sigma squared. Now, if you just want sigma for the standard deviation, then you take the square root. So this square number right here, if you pull the square root, then you just have sigma. And we'll walk through this. It is customary to get the 95% confidence limit. So 95% confidence limit is what we want. It is customary then to take not just one sigma, because one sigma will only give you 66.67% of the data. So you want to have more inclusion of your data set. You want 95% confidence limits, and for that you need to take the sigma times 1.96 to get 95% confidence limits. So you need to multiply your calculated sigma times 1.96 to get confidence limits of 95%, which is customary. And you can read through this here. There's some more explanation about this, why we do have to do the x bar, the average plus minus 1.96 times the standard deviation. That will give you the 95% confidence limits, and that is customary. You cannot process your data with such low confidence limits with just one standard deviation. That is not enough inclusion, and everybody will reject your paper, your publication, or your claims if you calculate with just 1 times sigma. If you want to do it extra careful, then you can do 3 times sigma. That will give you 99% confidence limits, but that usually gives you huge error bars, and it makes it difficult to prove statistical significance. But of course, if you have some really strong data sets, you can be going to 3 times the standard deviation. Anyway, here is a data set that calculates everything out for you, and you can take a look at that. So here you have a control group. These are people just that are exercising, and then you have here the increase in heart rate. So there's heart rates and 2 groups of males. One with normal, that will be no history of heart disease, and then you have males that have recovered from myocardial infarction. So that means they had a heart attack. So this is your experimental group, and you want to see if there is a significant difference in the heart rate of these individuals. Your N is 11, so it means you have 11 males that you're testing in each group, and then here are your data points, the 11 data points. So you will add them up. That's A. So that will give you the sum of the data. That's 780 versus 774. And the average is 70.9 and 70.4 here. Then you calculate your B. That's the sum of the squares of the values. And then you calculate your C, where you're comparing the sum of the squares versus the square of the sum, and you subtract that, and then you find your C value, and that's this one right here for the 2 respective groups. And then you calculate your sigma, which is sort of how much variation you have in your sample, and then you can plug all of this into a t-test, a t-formula. So this, once you have your averages, your C calculated, and the N you already know because that's the number of data points you have. You can plug this into this formula, and then you calculate your T. And your T calculated in this case is 0.136, which is very, very small. And so if we have a T that's that small, then you just have to look at your data table, the degree of freedom for the data set that you have, which is N minus 1. So we have 2 sets of data, N1 or N2 minus 1, whichever one is smaller, and then you have to go to the DF table, and I'll show you that. Here in the appendix handout, you have appendix B, and it's a T table, and it gives you the degree of freedom. Now remember, degree of freedom is the smaller of your data sets minus 1. So in our case, it was 11 minus 1 is 10, and so our DF is 2.23. So here's our 2.23, which is the degree of freedom. Now we just have to take a look at whether our calculated t is smaller or bigger than the cutoff degree of freedom. And we find that 0.136 is definitely smaller than 2.23. And so then we're going to put this into our data table and find that there is no significant difference